Hello everyone and welcome back. So today what we are going to do is we are going to do some additional examples on 2D frames and beams. And actually the best way to like learn more about structural analysis is actually to do different examples, because through different examples I can introduce different concepts. So let's get started. And to recap, some of the important things that we have done is actually I introduced these beam stiffness coefficients and the physical meaning of these coefficients. So these are important numbers to remember. So we are again going to use these ideas. So the idea was, okay, we can take these beams and we can just rotate them and it just becomes a column stiffness coefficients. So beam and columns are like related because these are actually the same things. But in one case we look at them in the horizontal fashion, in the other case they are just vertical, and so we can use these numbers directly for columns. And similarly we can do for the degrees of freedom at the J node. So this is the degrees of freedom at the J node on the beams for the beams, and we can just rotate them and get the stiffness coefficients for the column. And so these are the important stiffness coefficients that we are going to use throughout the lecture today. So it's very important that you understand these stiffness coefficients. So these are easy to remember also, and it's actually if you have difficulty in remembering, I would say that probably print these for sheets, so they're like always in front of you when you're doing any of these problems actually. And it will also help you to move through the lecture in the smooth way. So I will definitely ask you to print these 4 sheets. And then sometimes we will also use the truss element stiffness, and typically that will be used if we have a brace member. So whenever we have a brace member, you can do it directly also, but this comes in handy if you forget like what are these stiffness coefficients and where they're located. And the first problem that we want to work is actually the beam structure with axial forces. So we have already considered a beam element with axial degrees of freedom, where I have introduced like a ui and uj. These are the axial degrees of freedom, ui and uj, and vi theta I, vj theta j were the flexural degrees of freedom. And for a beam member, these axial and flexural degrees of freedom are uncoupled. So the flexural motion does not interfere with the axial motion. So they are like two motions are uncoupled. But actually, this is only uncoupled for beam members that are horizontal. If it's a frame member, then they're coupled. Okay. For the frame member that is inclined, when the member can be inclined at any angle, then the axial and flexural degrees of freedom are coupled in that case, because those degrees of freedom are in the global system. So in the global system, for an inclined member, the degrees of freedom will be coupled. But if we look in the local system, that is true for beam members, these degrees of freedom are uncoupled. And this was the stiffness matrix, 6x6 stiffness matrix, when we considered the axial degrees of freedom. And actually the axial coefficients are stiffness coefficients are EA by L. So those are the same stiffness coefficients that we use for the bar members. So this is a 6x1 force vector for beam member. This is pxi, pyi, mi, pxj, pyj, mj, stiffness matrix times displacement vector plus fixed end forces. Okay. So this is the complete equilibrium for a single element. And now we want to go ahead and solve a problem that includes a beam system with some axial forces acting on it. So this is the example that I want to consider first. So in this case, this beam has 3 spans. So it's a multi-span beam. The span is AB, BC, and CD, 3 spans. And the interesting thing here is on span BC, there is some horizontal traction acting. So this is the horizontal traction of 2 kip per foot. And there is some nodal load in the axial direction that is acting at C, that is 5 kips. Okay. So in earlier problems, if you recall on beams, we never applied any horizontal forces. So beam was only going on flexural deformations in that case. But for this problem, we are also applying horizontal forces. It means that this system will go both flexural and axial deformations. So let's go ahead and solve this problem. So the properties are given to us, E, I, A, and L. So length, L is 12 feet for all members, so length is fixed. The important thing to remember for this problem is that I is different. For span AB, I and A are given to us as I and A. For BC is actually twice of I and twice of A. So whatever this number is, A for BC is 2A. And for CD, the properties are I and A. So it's important to remember that to use the correct properties for different members. And we want to find the unknown displacements and member forces in this case. So what you're going to do is we're going to first discretize the system and assign the free degrees of freedom. So the free degrees of freedom in this case are axial degree of freedom here, rotation here. So if I go back, so axial deformation at B and the rotation at B, these are the free degrees of freedom at node B. And actually I'm discretizing into 3 elements. So first element is AB, then BC, and then CD. And the free degrees of freedom at node C are actually U3. So this is the horizontal displacement at C and the rotation at C. There is no vertical motion at B or C. So those are 0. Okay, those are supported degrees of freedom. So I just label the free degrees of freedom in this case. And then we can go ahead and solve the system. So there are 2 ways of solving it. One way is actually we can go and find the element stiffness matrices, like 6x6 matrices for all these members, and then assemble the global system and solve that system. The other way is a more direct way, where we just set up the system that is needed to be solved, the smallest system that is needed to be solved, and then just solve and then find the stiffness coefficients directly without like going through that element stiffness matrices algebra. So let's try to solve this problem by using a more direct and short method. So here the problem that we have to solve is PF is equal to KF, UF plus POF. So POF is PO1, PO2, PO3, PO4, and there are 4 free degrees of freedom. And the PF is P1, P2, P3, P4. In this case, supported degrees of freedom are all 0. So KFS US term is not needed. Okay, so US is all 0 because all the degrees of freedom are supported and there is no support settlement. Clearly, P1, P2, P3, P4 are, so you can see that P1 is the axial force here is 0, P2 is 25, P3 is 5, and P4 is the movement here that is 0. So so we already know what is PF, and then we have to find KFF. And to find KFF, we can go through the usual process. We'll take the first degree of freedom, displace it by 1 unit, and then find all the stiffness coefficients that are needed. And then we will take the second degree of freedom, displace it by 1 unit, and find the stiffness coefficients that are needed, and so on and so forth. So we have to do this process like 4 times because there are 4 free degrees of freedom. So this is the first degree of freedom. So you can think like a first degree of freedom is the axial deformation. So this is because this is a axial degree of freedom. So you can see that both member AB and BC is only undergoing axial deformations. Okay, so this is U1 is equal to 1, and we want to find K11, K21, K31, and K41. So K11 comes from EA by L for member AB and EA by L for member BC. Okay, so it's we have to add these contribution together. So you can think like you're trying to stretch this bar and compress this bar, and K11 is the total force to do that. And what you have to remember is that for member BC, A is actually twice the A. So this EA by L becomes 2EA by L plus EA by L for AB. So the final calculation will give you 3EA by L. Okay, if we try to calculate in terms of EA and L. So this is the calculation. K21 is the movement. But in this displaced configuration, you can clearly see that both these members, AB and BC, are only undergoing axial deformation. There is no flexure. So K21 is the movement that can only come from flexure. So K21 is going to be 0. K31 is coming from the member BC. So K31 is minus EA by L for member BC. The reason is because if you apply the force at B and So the force at B in member BC will be EA by L in the X direction. So at C, it should be in the minus X direction or in the opposite direction, and that should be EA by L for member BC. It's minus 2EA by L because A is 2A for this member BC, okay? So if you have trouble in getting this thing, you can always draw a free body diagram of member BC, and you will see that at end C, this is the force that is needed. And this is actually how this calculation is done. And K41 again is the moment, but the moment is 0 because there is no flexure anywhere. So there's no moment. And of course, the member CD is not deforming. So CD is not participating in any of these calculations. So this gives the first column of KFF, and then we can find the second column of KFF. We take the second degree of freedom, that is the rotation, and we rotate the degree of freedom by 1 unit. So in this case, these two beam members will get rotated, member AB and member BC. And the first entry come by symmetry. So K12 is K21. We are not going to calculate it again. K22 is 4EI by L for member AB and 4EI by L for member BC. So you have to go back and check the stiffness coefficients for beams, and you will see that these are the stiffness coefficients. Again, you have to be careful with the algebra. I is actually 2I for BC. So this becomes 4 times 2, 8 EI by L that comes from BC, plus 4 EI by L from member AB. So the final calculation is actually 12 EI by L, 8 EI by L plus 4 EI by L. And that's how we get 12 EI by L, and that is K22. K32 is the axial force at C. And that can only come from this beam BC because beam CD is not even deforming. So there is no forces in beam CD. And clearly, if you go back and check the stiffness coefficients, this beam has 0 axial forces. So K32 is 0. K42 comes from member BC again. It's actually 2EI by L for BC. And because I is 2I, this calculation becomes 4EI by L. So this is how I got this number, 4EI by L. And then we went to the next degree of freedom, that is U3 is equal to 1. The first two entry, K13 and K23, come from symmetry. So we are not going to do this calculation again. K33, let's look at K33, how to get this. So you can see that in this case, we are taking this U3 degree of freedom and displacing it by 1 unit. So both members BC and CD are only under axial deformation. So K33 comes from EA by L for member BC plus EA by L for member CD. So we have to add these two contributions. Again, for member BC is 2A, so this calculation becomes 2EA by L plus EA by L for CD. So the total is actually 3EA by L. So this is K33. And K43 is the flex. It comes from, like, it's a movement. It can only come from flexure, but there's no flexure in these two members. So K43 is clearly 0. So there is no moment in these beams, okay? Because there is only axial forces in these beams in this configuration. And then we can calculate the final column of KFF. The first 3 entry comes from symmetry, so we are not going to calculate them again. And K44 is now we look at the U4 degree of freedom, that is the rotation. So we rotate both of these members by 1 radian. And K44 is 4 EI by L for member BC plus 4 EI by L for member CD. And again, we have to remember that for BC, I is actually 2I. So this becomes 8 EI by L plus 4 EI by L. This gives us 12 EI by L. So if we do the algebra correctly, we can get all the stiffness coefficients, and this completes the calculation of KFF. So now we have all the entries in KFF. And then we can go ahead and find what is the POF. So we have to calculate the fixed end forces. And in this case, there's loads acting on each of these spans. So we have to do the fixed end calculation for each of these spans. For span AB, there was a uniformly distributed vertical loads, and so these are the fixed end forces for this case. And I have shown these fixed end forces at the top to show what are the values. And the units I'm using here are kips and fit. So you can see that my units are in kip and kip for kip fit. Kip fit is the movement, and kips is actually the vertical forces here. And for the second span BC, in this case, there is a 2 kip per fit of axial traction. And so the numbers are minus tau L by 2, that gives minus 12 kips at end B and minus 12 kips at end C. So these are the fixed end forces in this case. And actually, the simple calculation is the span length is 12, so total force that is acting in the x direction is 2 times 12 is 24. So half of it goes to the B end and half of it goes to the C end to make it into equilibrium. Yes, so we are just doing actual equilibrium of span BC. So this is a simple calculation here. And similarly, these are the fixed end forces for span CD, where there is a vertical force acting at the center of this span. And now we have to just assemble these numbers in the right fashion. So we get PO1, PO2, PO3, PO4. So you can see that the first degree of freedom is the axial degree of freedom at B. So this is the at B, this minus 12 goes to the first degree of freedom. Second degree of freedom is this rotation or this movement. So this is the at B. So this is minus 24 goes to the second degree of freedom. And similarly, the 3 is the axial degree of freedom at C. So the 3 is actually this force here at C. And fourth is the rotation. So this is 15 is the fourth. This goes to the fourth degree of freedom, okay? And I put all these numbers in the right order. So this is how I get my POF. And once we have all these numbers, we can go ahead and do the algebra. So the algebra is PF. This is PF is equal to KFF, UF plus POF. And then we just go ahead and solve for U1, U2, U3, U4. So this is the answer. And my answers are in fit and radian because these were the units I was using. And so U1 is actually U at B. So it's the actual displacement at B. And U2 is the rotation at B. U3 is the actual displacement at C. And U4 is the rotation at C. So these are the 4 displacements that were needed for this problem. And after that, we want to find the member forces. So if we want to find the member forces, we have to use the 6x6 stiffness matrix, okay? Because all these forces are present in this case, okay? Axial forces are also present, so we have to find the 6x1 vector of member forces, and we have to take the stiffness matrix multiplied by the displacement vector for that member and add the fixed end forces, and that's how we'll get the member forces. So we have to do this calculation for each of these members. So let's do for member AB. For member AB, this is the stiffness matrix. And for the B member, the left node is always the I node and the right node is always the J node. So this is the I node, this is the J node, and we want to find the displacements. Ui, Vi, theta I are the displacement at I node, but this node was fixed, okay? So all this Ui, Vi, theta I were all 0. Uj was U1, Vj was 0 because it was a vertical displacement at B. And theta j was rotation at B, so this is U2. So we have to plug in the right values of U1 and U2 and add the fixed end forces in the right order. So these numbers we have already calculated. So these numbers are Pxi, Pyi, Mi, Pxj, Pyj, Mj. So this comes from here. So this comes from this fixed end forces. You can see that I have not drawn any axial forces here because axial forces are 0. Okay, so they are there, but they're 0. But I didn't put any axial forces for span AB, but they're there. So they're 0. So you can see the number should be 0, 12, 24, and 0, 12, minus 24 in that order. And that's how I got this. And we do the calculation. These are the member forces. And I put here, I also show all the free body diagram for this span AB. And all these forces should be under equilibrium. And clearly you can see that this member is actually under tension of 14 kips, okay? Of course, there's a shear force and moment also acting on this member, but so we can do the calculation if we need the shear force and or bending moment diagrams for the member. And for member BC, we can again do the calculation for member forces. One important thing to remember is that I for this member was different. Okay, so the stiffness matrix is different for this member. So it's like twice the stiffness matrix for the previous member. And in this case, B node is the I node and the C node is the J node. And the calculation is done. So UI is actually U1, VI is 0, theta I is U2, UJ degree of freedom is U3, VJ is vertical degree of freedom at C, that is 0, and theta J is U4. So theta J is this, U4 is the rotation degree of freedom. And then we have to add the fixed end forces. So this fixed end forces come from the span BC. So if we go back and look at the span BC, you can see that there is only axial forces. So shear and movement are all 0 in this case. Okay, they're there, but I have not drawn it because they're 0. So the forces should be 12, 0, 0, and minus 12, 0, 0, and minus 12, 0, 0. And so these are the numbers in order. So PXI, PY, I, MI, PXJ, PYJ, MJ. So this is how these forces are written. And then we did the calculation and we find the fixed end forces here. And after this fixed end forces calculation, this is the total member forces. And I'm also showing you here the equilibrium for this member BC. In this case, you can see that the axial forces actually in this member is changing. So it's varying. So, but we can draw the bending force or shear force or axial force diagram if needed. But these are the member forces and they are under equilibrium. So you can check the equilibrium of these forces if you want to check. And finally, for member CD, we have to do the similar calculation. In this case, I node is C and the J node is at D. And the stiffness matrix is the same for member AB because those are the same properties that were used for span AB and CD. So this is the same stiffness matrix, but we have to put the right degrees of freedom. In this case, the J degree of freedom, this was all fixed. So UJ, VJ, and theta J is 0. And UI, VI, theta I. So in this case, UI is U3, VI is vertical displacement at C, that is 0, and theta I is U4. So theta I is the rotation at 4. But we have to also add the fixed end forces that comes from CD. Again, so PXI and PYI was 0. So X component of fixed end forces was 0. So this was the fixed end forces. I have not drawn the X component because they were 0. But then the number should be 0, 5, 15 and 0, 5, minus 15. And this is the order the fixed end forces should be in. And after we add these two contributions, we'll get the member forces. And this also shows the equilibrium of this member. And clearly, in this member is under tension, under compression, and the compression is 15 kips actually. So it's very easy to see the compressive force is 15 kips in this member. And you can check the equilibrium of this member, and this member should also be under equilibrium. Finally, I have also drawn the displaced configuration or the deformed shape of this beam member to show you how this beam is deforming. But the displacements are really small, so I have to use a large magnification factor of 200 to show you how the displaced shape looks like. And typically that is true in structures. Usually you cannot visually see the deformation in the beams or columns. They're very small, but if you magnify it, you can see like how the system is deforming. Because they're all very small elastic deformations, it's very difficult to visually see them. And that's the reason there was a option of putting a magnification factor in the MATLAB code that I have given you. And you can actually solve this problem yourself with the MATLAB code that you have, and you should be able to get the same answers. And the next problem that I want to do is a two-way frame. So this is a example in which I have the frame has two bays, and there is a brace member in one of the frame, and there is also at F there is a spring. So you can think that this is some kind of a spring. This F, the joint at F is connected to some kind of horizontal spring, and the spring stiffness is K sub S. And in this problem, what we want to do is we want to find the KFF of this there's a typo here. This should be two bay frame, not the two-story frame. Two bay frame in terms of E, I, A, and L. So, and we are also provided with this information that area of brace is like 4 times A, and the spring stiffness is 3 EA by L. Okay, so these properties are provided to us. The height is L, the span length is also L, but the properties of these members are different. So, and they are actually shown next to the member. So some members have different A's and different I's. Okay, so when we are doing the calculation, we have to take into account different properties. And so let's get started. So first we want to discretize the system and assign the degrees of freedom. So in this case, this is the discretization. So there are like 3 columns, 2 beams, and 1 brace member. And these are the degrees of freedom, 3 degrees of freedom, because we are interested in KFF. So I'm only labeling the free degrees of freedom. So the free degrees of freedom are U1, U2, U3. So 3 degrees of freedom at D, 3 degrees of freedom at E, and 3 degrees of freedom at F here. So there are in total 9 free degrees of freedom. And again, remember that because for the brace member, I don't consider like a rotational degree of freedom, because we know that that is always 0. So I'm not introducing the rotational degrees of freedom for the brace member. Okay, so these are the free degrees of freedom that we need to consider for this problem. And now we want to find what's KFF. And what we want to do is we want to follow the same ideas that we were following in the previous lecture, or even for the beams also that we just covered. We will take a degree of freedom, displace it by 1 unit, and find all the forces, and that corresponds to the stiffness coefficients in that configuration. So in this case, you can think that we have to do this exercise 9 times, because there are 9 columns in a stiffness matrix. But we will always also use the property of symmetry. So we will some of the coefficients we will just get by symmetry. Okay, so it looks like a long process, but it's not, because a lot of coefficients just comes from symmetry. And the other reason of applying this idea is because it helps us to think more in a more about how the forces are transferred within the structure, how these degrees of freedom connected, and how they influence each other. Okay, so this is a really interesting way of solving the problem, or how to come up with the stiffness matrix in a direct way. So let's get started. So this is the U1 is equal to 1 degree of freedom. So let's see what's happening in this degree of freedom. So we take this horizontal displacement is at D is 1. So you can see that the first thing you want to think about, how many members are actually deforming. So you can see that in this case, the beam D is deforming and the column AD is deforming. None of the other members are deforming. So whatever these forces are, these stiffness coefficients are, they will only come from the forces that are in this column and in this beam member. So that is the first thing. So always remember, first thing, try to figure out how many members are deforming in this in a particular configuration. And the second thing, you want to think about how those members are deforming. So you can see that this beam is actually only undergoing axial deformation, and the column is under flexure, because this is one of the flexural modes. So if you go back to those columns, let me show you. So this is this. I have to go back to the one of the earlier slides. Actually, this column is like this. So this is this flexural mode actually. Okay. So all those stiffness coefficients are actually here for that column, that configure for that deformation mode. So anyways, so this is what those numbers will come from, that mode, and that's the reason I want you to like print those sheets, so you have those modes handy, so you can directly put some of the numbers directly from those sheets. Now we want to get all those stiffness coefficients. So we start with K11. So K11 is actually will come from this column and this beam. So the column contribution is actually 12 VI by L of column AD, because that's a flexural, and EA by L of member DE. DE is a beam member in this case. So you can see that if I simplify the algebra, for column I is I, and so it's just this number remains 12 EI by L, but A for DE is actually 2A. So I have to put 2A here. This number becomes 2EA by L. So this is K11. K21 is the vertical force at D. Clearly, there's no vertical force in this beam member because the beam member is under axial deformation, and clearly there is no vertical force in this column also because column is under flexure. So K21 is 0. K31 is the moment, and it comes only from this column because this beam is under axial deformation. So there is no flexure there is no movement in this beam. So K31 comes from the column, and the number is 6 EI by L square of AD. This is only 6 EI by L square. And K41 comes from this member DE, and this is actually minus EA by L of DE, but A is 2A, so it becomes minus 2EA by L. And you can draw the free body diagram because you push this here with 2EA by L, the force here should be minus 2EA by L to keep this beam under equilibrium. And clearly K51 and K61 will be 0 because this beam does not have any axial force or moments. And all these other 3 remaining coefficients will be 0 because none of these members are actually deforming. So there are no forces at this node. So you can see that if we try to build the stiffness coefficients like this way, this gives a very important physical understanding how these forces are connected and things like that. So this is an interesting way to build stiffness matrices. So we can directly figure out which stiffness coefficients should be 0 or not 0. So let's go ahead and finish this exercise for the second degree of freedom. So second degree of freedom is the axial degree of freedom for member AD and the flexural degree of freedom for member DE. So this is U2 is equal to 1. So it's a vertical degree of freedom. So the first K12 is K21. It's coming from symmetry. So we are going to start with K22. So K22 is 12 EI by L cube of DE. So this is coming from flexure of the beam plus EA by L of AD. This is coming from axial load, the axial deformation of this column here. And if we simplify this expression, I is actually 2I for DE. So this first term becomes 24 EI by L cube, and then the second term remains EA by L. K32 comes only from this beam because the column is under axial deformation. So this is 6 EI by L square for DE, but I is 2I, so this becomes 12 EI by L square. And K52 is actually coming again from this beam DE, and this is minus 12 EI by L cube for DE, and this is just minus 24 EI by L cube because I is 2I. K62 again comes from DE, the beam DE, and again I is 2I, so this becomes 12 EI by L square. K42 is going to be 0 because there is no axial force in this beam. And all these other 3 numbers, 7.2, 8.2, 9.2 are going to be 0 because none of these members are actually deforming. So there are no forces here. So this is the calculation for the second degree of freedom. So we get the second column of KFF. This is the calculation for the third degree of freedom. Third degree of freedom was rotation. The first 2 entry comes by symmetry, so we are not going to calculate it. So K33, to get K33, you have to remember that we have to rotate 2 of these members. So it's going to be a contribution of 4EA by L for AD for this column plus 4EA by L of this beam, and that is DE. And we have to remember that for DE, I is equal to 2I. So this becomes 8EI by L plus 4EI by L. So K33 finally is actually 12 EI by L. So this is the stiffness coefficient for K33 degree of freedom, and then we can go ahead and find the other degrees, other stiffness coefficients. Clearly K43 is going to be 0 because there is no axial force in this beam, and 7.3, 8.3, 9.3 are again 0 because there is no deformations here. And finally, and none of these, so all these members have no forces. So all these numbers are going to be 0. And K53 and K63 are not going to be 0. They will come from this beam DE. So K53 is actually minus 6 EI by L square for DE. You can go and look at the stiffness coefficient for beam. This is the number. And but we have to put I is equal to 2I. So this becomes minus 12 EI by L square for this member. And K63 is 2 EI by L for DE. So because I is equal to 2I, this becomes 4 EI by L. And so now we have finished the third column of KFF. Let's go and try to do the fourth column of KFF. For the fourth column, we put U4 is equal to 1. So in this case, you can see that there are multiple members that are deforming. Beam DE is deforming, beam EF is deforming, column BE is deforming, and brace AE is also deforming. Okay, so you can see that K44 contribution will come from 4 of these numbers. The first 3 numbers come by symmetry, so we are not going to do the calculation again. So let's see. Let's start with K44. So K44, the first contribution is I'm just putting like the actual contribution for this member DE. This is EA by L of DE plus EA by L of this beam EF. So these are the 2 actual contributions plus 12 EI by L cube for member BE. So this is for column. So because column is under flexure, so this is 12 EI by L cube. Plus we have to add the contribution of this brace. For this brace, I'm considering A node as the I node and E node as the J node. So you can think that angle theta is 45 degrees. So C square, S square is both 0.5. And actually, so what we have to put, if we want to pick up the, so in this case, what do you think? You can think that this is the UI, VI, UJ, VJ. So UJ degree of freedom is corresponding to U4 is equal to 1. So I have to pick up K33 entry from the, let's say, this stiffness matrix, K33. So this is the entry that I have to pick up will be C square EA by L. So C square is actually 0.5 times AE by L for this member. Okay, so that's the number I want to pick up. So I picked up that number and put in here. So this is 0.5 times, but EA by L, A was 4A. So I have to put like A of 4A, and I do the algebra for this expression. This gives us, this is actually, so I have to be careful because DEA was 2A. So this is 2EA by L plus EA by L. This gives us 3EA by L plus this is 2EA by L. So finally we end up with 5EA by L. And this 12EA by L cube, I is 3I for member BE. So 12 times 3 becomes 36. So K44 is actually 36 EI by L cube plus 5 EA by L. So this is the calculation for K44. K54, again, you can check. This number is actually 0.5 times 4 EA by L. So it's actually same as this, but actually you can pick up the right entry from the stiffness matrix of this truss element. And then this number is going to be 2 EA by L. Okay, so this number is actually, this should be, let me show you where this number should be. So this, I'm picking up this number is actually, this number should be in the, let me go back. This is CS. So because I'm picking up the VJ degree of freedom. Okay, so this should be CSAEA by L. Okay. And then K64 only comes from this column here. Okay, the beam does not have any flexure, so beam does not have any movements. Of course, the truss member or this brace member does not have any movement. So the moment K64 can only come from this column BE, and the contribution is 6 EI by L square for BE, but I is 3I, so this number becomes 18 EI by L square. And Then K74 is the axial force in EF. So it's actually minus EA by L of EF. So this remains minus EA by L. And 8,4 and 9,4 are 0 because there's no moment in this beam. And these two column and the spring member does not have any forces. So 8,4, 9,4 remains 0. And then we go to the fifth degree of freedom, U5 is equal to 1. The first 4 entries come by symmetry, so we are not going to do the calculation again. And you can see that in this case, what's happening, these two beams are undergoing flexure, and the column is undergoing under axial deformation, and of course, the truss is under axial deformation. So the contribution from this column is actually EA by L of BE, plus the contribution of this beam is 12 EI by L cube by of DE. Contribution of EF is 12 EI by L cube of EF, plus this contribution of this truss member is actually K4 entry from this truss element stiffness matrix. Okay, so 4 entry I have to pick up. So 4 entry is going to be S square. So S square is actually still 0.5, and EA by L is, I have to put the right area. Area is 4 times A. So this is the contribution. And I have to again do the algebra carefully. For BE, A is actually 3A. So I have to put 3A plus 2A. So this becomes 5EA by L. 5EA by L. And of course, I have to do the algebra here also carefully because I is equal to 2I. So this is 2I, so it becomes 24 plus 12, 36. So 36 EI by L cube. So this gives us K55, and K65 comes from this beam DE and EF. Okay, so this K65 is the moment. The moment column does not have any movement, and the brace does not have any movement. It only comes from these two beams. And the calculation is minus 6 EI by L square for DE plus 6 EI by L square for EF. But for DE, I is actually 2I. So this is actually minus 12 EI by L square plus 6 EI by L square. So actually EF, so there is a minus sign that is missing. It should be minus 6 EI by L square. So I made a small mistake here. I'll fix it. Okay, I'll fix the slide. This number should be minus 6 EI by L square, K65. K75 is actually the horizontal force here, and because this beam does not have any horizontal force, this is 0. K85, K95 come from this member EF, and then these are the numbers. So it's 12 EI by L cube for EF and 6 EI by L square for EF. So these are the two numbers. So this is how we can get all the stiffness coefficients in this configuration. Next is U6 is equal to 1. And U6 is the rotation degree of freedom at E. So when we rotate the members here, an important thing to remember that, see, there is no rotation degree of freedom in this truss member. So the truss member does not get rotated. Only the beam and column members get rotated, okay? So in this case, the first 5 comes from symmetry stiffness coefficients. So we don't worry about those first 5 stiffness coefficients. We start with K66. So K66 is 4 EI by L for BE, this column, plus 4 EI by L for DE, this beam, plus 4 EI by L of this beam, EF. So we have to just do the algebra carefully because I is different for each of these cases. So actually it turns out 3I plus 2I plus I. So it's actually 6I. 6 times 4 is 24. So it's actually K66 is 24 EI by L. So this is how I get this number. K76 is the horizontal force here. This is going to be 0 because there is no horizontal force in this beam. And K86 and 96 come from this beam EF. So 86 is minus 6 EI by L square of EF. So this is just minus 6 EI by L square. And K96 is 2 EI by L of EF. So this is just 2 EI by L. So this is how we can get the entries in the 6th column. Again, you can see that, a lot of entries we are just getting from symmetry. So we are not really doing the calculation for those stiffness coefficients. We are just doing calculations. For example, in this case, we just did the calculation for 1, 2, 3, 4 entries. And U7 is equal to 1 is the horizontal displacement at F. In this case, you can see that this beam EF is going axial deformation. This column is also going flexural deformation, and this spring is also deforming. So this is where you have to remember the effect of the spring. So in this case, you can think that the spring is also undergoing some kind of compression. And of course, the first 6 entries we are getting by symmetry, and we are starting with just K77 in this case. So K77 is EA by L of this beam. So EA by L of EF plus 12 EI by L cube of this column CD plus KS. Okay, because KS is the stiffness of the spring, and KS is given to us is like 3 EA by L. So we have to just put this number here and do the algebra. So if we do the algebra, this becomes 12 EI by L cube plus 4 EA by L. This is K77. K87 is the vertical force here, and you can see that there's no vertical force in this column or this beam or in this spring in this configuration. So K87 is 0. K97 only comes from this column because this beam does not have any flexure, so there is no moment in this beam, and the spring only has like a horizontal force. There is no moment in the spring also. So K97 comes from this column. So this is 6 EI by L square CF. This is 6 EI by L square. K8 is equal to 1 is the vertical displacement at F. And in this case, you can see that only the beam and column is participating. The spring does not have a stiffness in the vertical direction, okay? So I'm not deforming the spring anymore. So spring only acts in the horizontal direction. So spring does not act in the vertical direction because this is a horizontal spring. So in this case, K of the first 7 entries come from the symmetry. We are starting with K88. So K88 is actually EA by L of CF. So this is the contribution of column, that is axial deformation, plus 12 EI by L cube of EF, that is flexure. So this is the total sum is 12 EI by L cube plus EA by L. And K98 comes from this beam, and this is minus 6 EI by L square of EF. This is just minus 6 EI by L square. So this is the contribution of this beam. Again, remember that column does not have any flexure, so there is no movement in this column, only the axial forces in this column in this configuration. And then we have the final configuration, that is U9 is equal to 1. It's a rotational degree of freedom at F. So in this case, we have to rotate 2 members, EF and FCF. So K99, see, all the first 8 entries come by symmetry. So we just want just one number, K99 in this configuration. So this is 4 EI by L of EF plus 4 EI by L of CF, and I is I for both members. So this calculation just gives us 8 EI by L. So using this calculations, we can find the entire KFF of the structure, and we can put everything together. So I'm just writing the symmetric part of KFF, and this is the KFF of the entire structure. This is a 9 by 9 stiffness matrix, okay? And this finishes this problem, and I hope you get some idea, like to understand more deeply what's happening and to understand the physical meaning of these stiffness coefficients. And the last example for our class is actually a 2-story frame. And this is, we are going to use the same ideas that we have used for the last 2 problems, but this is a little bit more interesting problem because I have introduced like a bracing here and also a hinge here. And again, in this case, we want to find KFF in terms of E, I, A, and L. And for simplicity, in this case, we are assuming that area of all beams and columns are A. So I'm not changing the areas of beams and columns. I is changing. So we are still changing the moment of inertia, okay? So I is different, and they're labeled near the members. But the areas, we are assuming they're all A. And the area of the bracing, we are assuming it's 2A. And we want to find KFF for this system. And actually, these 2 examples, one with 2 bays and one with 2 stories, are actually capturing most important configuration for like frames for movement frames and brace frames, because all the like we can easily extend to 3-story, 4-story, or multi-story, multi-bay frames. Well, the ideas will remain the same. Okay, so all the ideas that are in example 2 and 3 can be extended to any number of stories. So size of the problem doesn't matter. What is important is the important concept behind how to figure out or how to understand the stiffness coefficients for these structures. So let's try to build the KFF of this system. And first, let's try to discretize this system and assign the degrees of freedom. So in this case, actually, there are like 13 degrees of freedom. So these are the degrees of freedom. So at this joint, the degrees of freedom are U1, U2, U3. At this joint, the degrees of freedom are U4, U5, U6. So there are 3 degrees of freedom at each of these points. And because of the hinge, there is 2 rotation degrees of freedom. So U7, U8, U9, and then U10 at the right of the hinge. And then U11, U12, U13, okay? So they are like 13 degrees of freedom. And we want to build a stiffness matrix for this case. So you can see that now we have to display the structure 13 times. 1 for each degree of freedom, and find the corresponding column for the KFF. So this process is a little bit more involved. So let's go through it carefully. But you will see that once you have those stiffness coefficients ready, it's just a matter of algebra and careful thinking. And actually, sometimes once you get good at it, you don't really have to draw these figures. You can actually think carefully. What are these numbers? And actually, you can get the numbers quickly. So it needs a little bit more practice. Okay, so. And anyways, anything you want to be good at, you have to practice to become really good at these things. And actually, if you think like if you want to become a good structural engineer, these are the things you need to understand deeply, and so you will really understand how the structure is behaving. So let's start with the first degree of freedom. In this case, U1 is equal to 1. So U1 is equal to 1 is the horizontal displacement at C. So in this case, you can see that the 2 columns are deforming, both the first story and second story column, and the beam is also deforming, and this truss member is also deforming. Okay, so they're like in total 4 members. So there's flexure in these 2 columns, and axial deformation in this beam, and of course the axial deformation in this brace. So to find K11, we have to add the contribution of all these things. So it's the contributions are 12 VI by L cube for AC, column AC, plus 12 VI by L cube for column CE, plus EA by L of beam CD, and plus the contribution of this bracing. And the contribution of this bracing is actually C square S square is actually 0.5, and times EA by L, and this is like 2 EA by L. And actually, you can get this number from the stiffness matrix of the truss. Okay, so you have to think carefully from where to pick it up and pick it up. So this is going to be, it depends on which node you're going to call it I and which node you're going to call it J, but you can check it out. This is the right number. And if we do the algebra, then we have to do the right algebra. A and C, so for AC, the I is 2I. So we have to put 2I here. So 12 times 2 will become 24 EI by L cube, plus 12 EI by L cube. So 24 plus 12 will become 36. And this is EA by L plus EA by L for here. So it becomes 2 EA by L. So this is how we get K11. K21, the contribution of K21, there is no axial forces in these 2 columns or in this beam. So K21 only comes from this brace, and the brace contribution I have shown in blue just to highlight what is the contribution that is coming from the brace. So you can pick up the correct entry from the brace, and if you check it out, this is just going to be half times EA by L, and this is going to be minus EA by L. Okay, there's a minus sign here, and I want you to think about yourself and how to pick this entry correctly from the stiffness matrix of the truss element. And if you think a little bit carefully, the negative sign should be there. And this is the K21. And K31 comes from, so K31 is the moment here. It comes from these 2 columns because the brace and the beam does not have any any movement. The beam is only going axial deformation, and the brace has no movement. So K31 is 6 CI by L square of AC minus 6 CI by L square of CE. And the important thing to remember is that I is equal to 2I for AC. So this becomes 12 VI by L square minus 6 CI by L square. So this calculation gives us 6 CI by L square. Okay. So now these are the entries at node C. See, there are a lot of zero entries here. For example, I put all these zero numbers here. So for example, all these numbers 13, 1, 12, 1, 11, 1. They're connected to these two members, to beam and columns. They're not even deforming. So these forces are all zero. So they're directly zero. Similarly, at D, only K41 is non-zero because that's the axial force in D. K51 and K61 are again zero. Okay. And K101 is zero. So there are a lot of zero entries that I just directly put down here because K101 comes from this beam here, and this beam is not even deforming. So the only non-zero entries here are K71. K71 comes from the column CE, and this is minus 12 VI by L cube of CE. So this is just minus 12 VI by L cube. And K81 is again zero because this is the axial load in this column. This is going to be zero. K91 is actually coming from this flexure of this column. This is minus 6 CI by L square of CE. This is minus 6 CI by L square. So now you can see that a lot of these entries are going to be zero of these stiffness coefficients. So I just put it in one single line. What are the zero entries? Okay. And this finishes up the first column of the stiffness matrix. In the second column of the stiffness matrix, we take the second degree of freedom to find the second column and displace it by 1 unit. The first entry come by symmetry, so we don't have to recompute it again. We start with K22. So K22 is a contribution of these two columns, one brace and one beam. Beam is under flexure, two columns are under axial deformation, and of course the brace is under axial deformation. So the contribution of beam is 12 VI by L cube, and then EA by L of AC and EA by L of CE plus this is the contribution of the brace in blue. And so we can do all the algebra, and the answer will be 12 VI by L cube plus 3 EA by L. And then K32 is a moment. It only comes from this beam because none of the other elements have movements in them. So K32 comes from the beam. Is 6 EI by L square for this beam. This is 6 EI by L square for CD. And K52, K42 is zero because there is no axial force on this beam. K52 and K62 come from this beam. So K52 and K62 come from this beam CD. And then if we look at the other degree of freedom, K72 is going to be zero. K92 is going to be zero because this column here is only undergoing axial deformations. K82 is not going to be zero. K82 is minus EI by L of CE. This just comes from the equilibrium of member CE. And this is minus EA by L. And again, all these numbers K 11, 2, 12, 2, and 32 are going to be zero because these two members are not even deforming. And again, K10, 2 is zero because this beam is not even deforming. So there's no forces here. And this is how we can get the second column of the stiffness matrix corresponding to this degree of freedom. And then there's a U3 is equal to 1. This is just a rotation. And when we are rotating this degree of freedom, you can see that I'm not rotating the brace member because brace member does not have any rotational stiffness. So there's no rotation in the brace member. So K33 rotation is always simple. These are just 4 EI by L for the members. So it's 4 EI by L for AC plus 4 EI by L for CE plus 4 EI for CD. But I is different for these members. So we have to just remember the calculation of that I is different. So I is actually 2I for AC. So we have to put 2I. So this is going to be 8 EI by L plus 4 EI by L plus 4 EI by L. So final calculation is 16 EI by L. K43 will come from this beam here, but beam does not have any axial forces. So K43 is going to be zero. K53 and K63 again comes from the beam CD. So these are the calculations. K63 is 2 EI by L, K53 is minus 6 EI by L square, and this is coming from the beam CD again. K73 and K93 comes from the beam or column CD, CE actually. K83 is going to be 0 because there is no axial force in this column CE. And we can calculate K73, K93 as 6 EI by L square and 2 EI by L. You can look at the column coefficients. These are the numbers. Again, K103 to K133, they're all 0 because none of these members are deforming. So all these forces are 0. So this completes the third degree of freedom. Let's go to the fourth degree of freedom. So fourth degree of freedom is actually a horizontal degree of freedom at D. So in this case, these two columns are deforming and this beam is deforming. And we want to calculate K44. There is no deformations in this brace. So brace is not contributing to this degree of freedom. So in this case, you can see that K44 is EA by L of CD. So this is the actual contribution from CD plus 12 VI L cube from BD. This is the flexure from this column and 12 VI by L cube of DF. So this is the flexure of this column here. Okay, so we have to do the algebra and remember that I is different for different members. So this is I is 3I for BD and this is just I. So it becomes 36 plus 12, 48 EI by L cube plus EA by L for this beam. K64 comes from these two columns. Beam does not contribute because beam does not have any moment. Beam only has axial forces. So it's actually it's actually 6 EI by L square for BD minus 6 EI by L square for DF. And if we do the calculation carefully, this is going to be 3I minus, so this is 3I, so this I is equal to 3I, so this becomes 18 EI by L square minus 6 EI by L square, so this becomes 12 EI by L square. And K11.4, K13.4, they're non-zero, so 12.4 is going to be 0 because this is the axial, and that comes from this column. This column does not have any axial force, like column DF does not have any axial force, but 11.4 and 13.4 you can calculate from this column here, and these are the numbers are minus 12 EI by L cube and 6 EI by L square. And all these numbers here, 7.4, 9.4, 8.4, 10.4, they're all 0 because these members are not even deforming. There are no forces here. So this is how we can get the fourth column of KFF. Next, this is the fifth column of KFF. So we take the fifth degree of freedom, that is a vertical displacement at D, and move it by 1 unit. So again, there are two columns that are deforming and one beam that is deforming. So these are the only members that will contribute to the stiffness coefficients. A lot of coefficients, let's say 1, 2, 3, 4. The first 4 coefficients come from symmetry, and these numbers here at E, like 7, 5, 9, 5, 8, 5, 10, 5, they will be all 0 because these members are not even deforming. And also K11.5 and K13.5, they will be 0. Only the axial force K12.5 will be non-zero because this column is only going axial deformation. So let's see the calculations here. So K55 is actually axial, so it's EA by L for BD, or plus EA by L for DF. So it should be there's a small mistake here. This number should be BD, not CD. I'll fix this typo. So it's EA by L for BD plus EA by L for DF plus 12 EA by L cube for this beam CD. And if we do the algebra, we should be able to get the right number. So this is 2 EA by L plus 12 EA by L cube. And K65 comes only from the beam. This column does not have any flexure, so there's no movement in the column. And this is minus 6 EI by L square and for CD, this is just minus 6 EI by L square. And K12.5 is minus EA by L for DF, because you pushed here up from with EA by L, so the force here should be in the negative direction, and this is EA by L. And other coefficients are, as we already talked, they're all 0. For the 6th degree of freedom, 6th degree of freedom is just a rotation. So you can see that there are 3 members that are rotating. So the first 5 stiffness coefficients come from symmetry, and K66 is 4 EI by L for BD plus 4 EI by L for CD and plus 4 EI by L for DF. And but the I is different for each I, so it's actually 3I, 4I, 5I. So 5 times 4, 20 EI by L. So that's the K66. And K76, 8, 6, 9, 6, 10, 6, they're all 0 because none of these members are deforming, so there's no forces here. K12.6 is also 0 because that's the axial force in this beam that will come from, and there's no axial force in this beam. K11.6 and 13.6 are not 0, that they still come from this member DF. So K11.6 is 6 EI by L square of DF, and K13.6 is 2 EI by L of DF. So this is the calculation. And again, you can always go and look at the stiffness coefficients for these beam and column members to get these numbers. So this is the calculation for the 6th degree of freedom, and this gives us the 6th column. Next, we go to the 7th column of the stiffness matrix. So in this case, U7 is equal to 1. That is horizontal displacement at E is equal to 1. And in this case, only 2 members are going to participate. One is the column CE, and one is the beam member EF. Clearly, the beam EF is under axial deformation, and the column CE is under flexure. Again, the first 6 coefficients come from symmetry, so we are not going to calculate them again. And K77 is EA by L of EF plus 12 EI by L cube of CE member. Again, there's a small typo here. This number should be EF, not DF, okay? So I will fix this typo, but the number is correct. So if we do the algebra, this is just EA by L plus 12 EI by L cube. And once we have this number, K12.7 and K13.7 will be 0 because the beam is under axial forces. K11.7 is not going to be 0. This is going to be minus EA by L for EF. I'll fix this typo of DF. It should be EF, not DF. And this is just minus EA by L. And again, K10.7 is going to be 0. Because this comes from this beam, the beam is under only axial deformation. There is no flexure. So the moment K10.7 is 0. K8.7 is again going to be 0 because that comes from the axial, and there is no axial force in this column, and there is only axial force in the beam, but it's in the horizontal direction. There is no vertical axial force. So K8.7 is going to be 0. K9.7 comes from this column here, and K9.7 we can do the algebra. This is 6 EI by L square for CE, and this is just 6 EI by L square. So K9.7 is not going to be 0. And these are the stiffness coefficients for the 7th column, and we can go ahead and do the calculation for the 9th column. For the 9th column, we take the vertical displacement at E and move it by 1 unit. So this is U8 is equal to 1. And again, the first 7 entries come by symmetry, and we start with K88. K88 is EA by L of CE. So this is the axial contribution from this column plus the flexural contribution from this beam. So this is 12 EI by L cube of EF. And this is just EA by L plus 12 EI by L cube. And then K10.8. So in this case, K9.8 is coming from the column. So K9.8 is 0 because the column is undergoing only axial forces. So there is no undergoing only axial deformation. So there is no there is no movement in the column. So K9.8 is going to be 0. But K tan 8 comes from the flexural of this beam. That is not going to be 0. So that is non-zero. So K tan 8 is 6 EI by L square of EF. And this is just 6 EI by L square. Again, K 11.8 is going to be 0 because there is no axial force in this beam EF. But K 12.8 and K 13.8 are non-zero, so we have to calculate them. So K 12.8 is minus 12 EI by L cube of EF, and K 13.8 is 6 EI by L square of EF. So these are the calculations. Okay. And so if you think very carefully, you should be able to get these numbers right. And of course, you can go back and look at the coefficient sheet to pull out all these numbers. Then we are doing the U9 degree of freedom is equal to 1. U9 is the rotation at E, but because of the hinge, these beams and columns can rotate independently. So in this case, U9 is only associated with the column. So I'm just rotating one column here. And the number that is needed is 4 EI by L for this column CE, and this is K99 is 4 EI by L. And you can see that K10.9, 11.9, 12.9, 39, they're all 0 because this beam is actually not even deforming in this configuration. And of course, this column is also not deforming. So there are no forces here. Okay. So this is a very straightforward degree of freedom. So only the K99 is this entry. Of course, the first 8 entries are coming by symmetry, so I'm not recalculating them again. This is U10 is equal to 1. Again, because of this internal hinge, this beam is rotating independently of this column here. And this is, I'm showing you K10 entry. So this is just a moment here. This is 4 EI by L for this beam here. So this is just 4 EI by L. And K1110 is the horizontal force that will come from this beam. This column is not deforming at all, so there's no forces in this column DF. And so K1011 is going to be 0. And K1210 and 1310 again come from this beam, and we can do the simple algebra to find these numbers. So K1210 is 6 EI by L square of EF. This is minus 6 EI by L square. And then K1310 is 2 EI by L of EF. This is just 2 EI by L. And the rest of the other numbers are coming from symmetry. So those we don't have to recompute. And then we have only 3 degrees of freedom left. And these are like straightforward degrees of freedom. This is like a U11 is equal to 1. So in this case, K1111 will come from this beam and this column. This is EA by L of this beam plus 12 EI by L cube for the column. So we get this numbers. And K12.1 is going to be 0 because there is no vertical forces in this column. And of course, there's no vertical forces in this beam. So K12.1 is 0. K13.11 come from this column here. So K13.11 is 6 EI by L square of DF. This is a 6. This is just 6 EI by L square. So this is how we get K13.11 entry. And then we have 2 more configurations to go. This is U12 is equal to 1. Again, this is a simple configuration. So K12.12 comes from axial in this column DF and the flexure in this beam EF. So this is EA by L of DF plus 12 EI by L cube of EF. So this is the calculation here. And K13.12 is coming from the flexural of the beam. The column does not contribute to 13.12. So this is minus 6 EI by L square of EF. So this is just minus 6 EI by L square. All the other numbers come from symmetry. So we didn't really recompute them. And this is the last column. U13 is equal to 1. So in this case, we are just rotating 2 members because the U13 is the rotation degree of freedom at F. And so you can see that in this case, the contribution is 4 EI by L of EF plus 4 EI by L of DF, and this just gives us 8 EI by L. So this finishes the computation of KFF for the system. So we can just put all the entries in a stiffness matrix. So this is a 13 by 13 stiffness matrix of this structure. And this is the last example in this lecture, and actually the last example for our class that I want to finish. And with this, I would like to end this lecture. But I also want to make some comments here. One important comment is you can see that in these beams and frame members, most of the members are like horizontal and vertical. So it turns out that whenever the members are horizontal and vertical, it's pretty straightforward to put the stiffness coefficients together. And so there is not much algebra involved. But if there are some members, some of these frame members are at like a different angle, then we have to do some more involved algebra. Then we have to use those coefficients, c square, s square, and so on and so forth. But as long as the members are like horizontal and vertical, these calculations are pretty simple, and you should be able to do by hand. And also this gives a physical better physical understanding and what is happening in a structure, how the forces are flowing within the structure. Okay. And I hope that this lecture also help you to work on your homework that is due on Monday. And let me know if you have any questions or if you need further clarifications on any of these issues, and I'll be very happy to help you or answer any of your questions. And with that, I would like to end this lecture. Bye-bye and have a wonderful day.